is supposed to do. I'm going to talk about inertial confinement fusion experiments at NIF. You're going to hear NIF over and over and over again. It means National Ignition Facility, or in layman's terms, Great Big Laser. NIF experiments have achieved fusion ignition in the laboratory. I mean, that's a big deal. It's the first time, well, we've had uncontrolled fusion, but nobody wants H-bombs going off in their backyard. So controlled fusion has been the goal since the magnetic fusion people started in the 50s. ICF is actually more recent than that. It started roughly in the 1970s. And it's very different, as I think you will see as I go through a description of how it works. So the NIF is located at Lawrence Livermore. It's the most energetic pulse laser in the world. We don't get a lot of pulses per day, so I'm trying to make it clear that I'm talking about this one pulse. You'll see that it's a very healthy pulse. The laser energy is converted to X-rays in the whole arm. I'm going to go into some more detail on all of this. The X-rays implode a capsule filled with deuterium and tritium. I don't know if anybody has ever talked about fusion cross sections to you, but deuterium plus tritium has by far the biggest cross section at some kind of a temperature that you could reach. And so everybody right now is planning on doing DT fusion. There's technically other things that could happen, but one of our early leaders of the program saw somebody talking about DD because tritium decays. And so it's not naturally occurring except through decays of materials. So you can make it from lithium, but DD would be cool because then there's an infinite supply. But my boss said, "What's the matter? DT isn't hard enough for you?" So we start talking about DT. And I've been there at the lab 40 years now, and he's right. DT was pretty darn hard. So once I've got the laser energy there, it is turned into X-rays, which bathe the capsule, and that implodes it. And we've actually produced fusion energy greater than the laser energy used to drive the target. Disclaimer, I'm not saying anything about the ratio of fusion energy out to wall plug energy to drive the laser, because this laser is not intended to be for fusion energy. It's intended to do scientific proof of principle and a whole bunch of high energy density experiments. And in point of fact, when we fire the laser, it's a glass medium, the glass gets heated up enough that you actually have to wait several hours because the glass expanded due to that heat, and you have to let it cool down before you can actually get the very precise aiming that we need. So totally happy that it is only a few shots per day because, you know, if you tried to do more shots, it'd be too hot and you wouldn't hit anything. There are several startup companies working on prototypes of inertial confinement fusion power plants. So the NIF laser delivers more energy per pulse than any other laser. And that's the figure of merit that we're after because we are not doing even a remotely continuous fusion source. You'll see that. So the glass is actually doped with neodymium. It's the neodymium that is the atomic level that's doing the lasing. That gas is pumped by flash lamps. So that's why he's not telling me how much energy you took out of the wall. Flash lamp is a continuum source, broadband. You can pump it only here in a little bitty chunk. Absolute guarantee to have horrible wall plug efficiency if you're using flash lamps. On another project, I'm working with a group at the lab who has come up with diode pumped solid state lasers. That can actually have reasonable efficiency. We're on a project where you use a laser much smaller than you, mind you, but able to bam, 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 shoot shots all day long. You use that to generate EUV, which is then used in lithography to make integrated circuits. And it turns out they're using a CO2 laser, which is, I think, better than our flash lamp laser in terms of wall plug efficiency. This is the third talk I might give if you guys are interested. And it turns out that when the Taiwanese started putting together the first plants that use these UV lasers, they actually had to put in several more power substations for their CO2 laser. If they used a laser like the one that the lab has been working on, they probably wouldn't have had to put those in. So there are paths forward to much more energy efficient lasers. So just don't ask what the wall plug efficiency is, because it's not relevant, because nobody is right I would ever try and do a power plant with that approach. So anyway, the glass is pumped by the flash lamps. The decay times of that level are moderately long. So you can get it excited and then organize it and fire your pulse through. It's not quite one pass, but it's like 1, 2, 3 pass amplification. So it doesn't have the mirrors bouncing it back and forth like your laser pointer would have. It's very definitely a one-pass laser. The laser wavelength from the glass is 1.05 microns, but we frequency triple the light using nonlinear crystals, which seemed kind of magical to me when I got there, because none of my classes had ever talked about nonlinear crystals. But we can actually get pretty high conversion efficiency up tripling the frequency. But we do lose some energy. Why do we lose the energy? Well, 0.35 micron light has lower laser plasma interactions than would occur at 1.05.
What does high energy laser translate to? Like, for example, is it like more success rate in like initiating the fusion, or like why do we want like higher energy lasers?
So basically, to get more energy out than you got in, you have to be very careful about how you design your target. And so you need to compress stuff up to high density while sort of minimizing the energy it takes to do that. And then you need to get spark plug ignition in the middle. I'll come back to this later. But the problem is, energetically, you can get this spark plug to ignite, but that's a small fraction of the total DT mass of the target. You have to get propagating fusion burn. And it turns out that the only way to get the burn is to have the fusion in the spark plug in the center bootstrap itself. Remember I said DT had the highest fusion cross-section? Well, it's not actually high enough. At the ignition temperature, you have to self-heat, and then the rate gets very fast. If your target is too small, the alpha particles just fly on out of the target, and you can't bootstrap. So there is a lower limit. And for a power plant, my own guess is that the 2 megajoule style laser that we have is not enough energy. You have to be firing your laser about 10 times per second to be able to economically produce electricity. And there's a whole bunch of other engineering stuff that goes before you get that point, but just simple back of the envelope things tell you that you need about 10 pulses per second. And so you're going to have your targets flying there 10 times per second. It's all very complicated. And it turns out that if you make the target somewhat bigger, it's considerably more forgiving. And I think if you want to fire off that many of them per day, you're going to want having it more forgiving by a somewhat high energy laser. You don't want to go too high in energy, because then you would have a power plant that produced so much power that if you converted it completely over to that, there'd be only a few in the country. And then if you get high winds going past the one in Colorado, 10% of the electricity in the country is gone. Boom, like that. And, the electrical utilities understand that part of it. So somewhere between 5 and 10 megajoules is what I suspect will turn out to be reasonable for a power plant, assuming that all the other engineering, fiddly little details, right? How can you make a gazillion almost perfect targets in a day, right? That sort of thing. Well, I'm ignoring that in this talk. The guys at those fusion startups are not ignoring it. And Livermore actually did some studies earlier, and so they knew what was going to be a lot of their biggest problems in trying to get to a power plant. And so they're working on it. It's an interesting point. The NIF ignition facility is housed in a building that was co-designed with the laser. And the issue is that the laser costs a lot of money, but so does a big building. And so you co-designed them, so you made the building as small as you could to fit the largest laser you could afford. So it's not something that would happen in one of the laboratories in this building. It's a big laser. That's the NIF laser building there. It's the size of 3 football fields. Once again, not that little laser pointer you use when you give a talk. The target chamber, I don't know if you can see my pointer, but it's over here, sort of on the lower right. That thing is actually 5 stories high. So even the target chamber is big. Here's one of the laser bays. The laser has 192 beams, but they're organized into 48 quads. Each quad is a 2x2 set of beams. And those beams propagate along together and enter the hole round through the same port. Remember, speed of light's pretty large. So a 20 nanosecond pulse is about 20 inches long. Remember I said this is not a steady state laser? Well, hell, we can't even fill up the whole laser with the pulse. There's just a little foot or two of it that has pulse in it when it goes through. So, just about as far from steady state as you can imagine.
I have to ask, so the speed is 1 foot per nanosecond, so why isn't it 20 feet?
Sorry, it's supposed to be 20 feet, but I got the wrong key. I didn't hit the shift key, probably because it was next to another key. So yes, 20 feet. The burn time is more like 100 picoseconds. So that's 1/10 of a foot. So light not going to move very far. You should actually be able to take that number and realize that in a moment, I'm going to show you that the target is pretty darn small. So here's the target chamber. They did use a fisheye lens, but there's a guy there pointed to by that little blue line. He really looks awfully small compared to that target chamber. He's actually standing in one of the ports through which the quad enters the target chamber. There's 48 quads. There's a whole lot more than 48 ports. Well, it turns out that it's crucial that we get a lot of good diagnostic results of what's happening. Laser diagnostics, X-ray diagnostics, fusion diagnostics. I mean, there's a whole bunch of them. And you sometimes need to look at stuff from several directions. And if we had the budget, we'd probably try and get them to do more, but they've come up with a truly amazing set of diagnostics. It's really impressive how much better the diagnostics are on NIF than the way they were on the laser that Livermore had put in just as I was hired. And so, like I said, the target's kind of small. And so, actually, light can almost cross the target in the course of the fusion burn. Yeah, it can cross it. Barely. So, very much not steady state. I keep mentioning this because some of you are bound to have sat in a bunch of magnetic fusion talks. It's not the same idea at all. Well, fusing DT, yes, but how you confine it long enough to burn it up is very, very different. So our targets have a capsule filled with DT, and the capsule rests inside a hole round. And actually, on that previous slide, the little thing that you can actually see is the hole round. The capsule would be inside of that and not visible from that view. So the hole round inner wall is either coated with gold or made of gold because gold has a high conversion efficiency between the laser light and X-rays. So 2 megajoules is a lot for a pulse laser, but as I mentioned, it's not really a lot for fusion ignition. So you want to get as much of that converted as you can. Gold's high Z, it has opacity at all wavelengths, so everything radiates, not like hydrogen where you get, 13.6 EV if you capture something from the continuum, period. And there's a big, huge gap around it, but gold's not that way. I don't know if you ever, I guess class has never covered it. We did the hydrogen atom, then mumbled about helium, I think. Well, the issue with gold is that you've got something like 50 electrons in there, and some of them are excited states, and they can couple with each other. I once asked an expert, well, if I wanted to model gold correctly, how many atomic configurations do I need to include? Oh, hard to say. Well, just approximately 1,000, 1,000,000, 1,000,000,000? Probably. I couldn't back him remotely into a corner. It turned out it wasn't 1,000,000,000, but it probably is around 1,000,000. So because you've got all these different configurations, you can get emission at many, many different wavelengths. And that's what we want to get good conversion efficiency.
And how much of the 2 megajoule laser energy actually convert to the X-ray energy?
During peak intensity, it's over 80%. I'm not sure if it's 90%
efficiency,
which is pretty darn amazing from my point of view.
And is the idea that the gold is like ablating away, or like is the gold gone after a shot?
Well, just try and guess what would happen if you were hit by a 10 to the 15 watt per square centimeter. Yeah.
Yeah. Is the whole all around like what's the rest of the all around made out of? Does it matter at all?
Actually, they kind of like other high Z stuff. There's been discussion of lead. To me, it seems more straightforward to have just the gold, but they think there are a few holes in the gold emission. They think if the stuff in the back were to plug those holes, sorry about that. Good. You might get a little bit more. At this point, it doesn't really seem to be crucial. And so the targets flip back and forth depending upon what they're doing. I just like to think of it as a gold target. The hole round will stick around for the duration of the laser pulse, but you've driven something called the Marshak wave into the gold. That's a radiation wave moving in there. And it's going to keep going until it breaks out the backside. And then even if the stuff is only at 50 electron volts, that's actually a high temperature. It will disassemble. So I can promise you that one. The target is mounted on a stalk, and the laser isn't supposed to hit the stalk. So somewhere down on the stalk is where you reach the limit of vaporization. But there isn't anything to do except potentially put a few diagnostic materials on the hole round walls and then collect the stuff that flies off. And you can potentially see radioisotopes and get their decays and get some ideas about neutron fluxes and such. Don't think we usually do that for fusion targets, but it might be a cool thing to do if you were interested in that material, because you can potentially hit it with a huge flux of neutrons.
Actually, if you have a chance to get a tour of the Neath building, they have a target before the shot and target after the shot. It does get destroyed. You can see that's on a display somewhere in the building.
Yeah, there's actually a little clamshell around the target because it needs to be at cryogenic temperatures. That flips out of the way. I don't remember if that survives or if it has to be replaced.
Part of it survived.
I'm pretty sure it doesn't survive if we get ignition, but in a non-ignition experiment, it might survive.
So in a power plant, not only are we dropping a DT pellet several times a second, but also a whole row.
So I obviously forgot a couple of bullet points. There are two approaches to inertial fusion: direct drive and indirect drive. Direct drive, all of the energy goes into the capsule, which is a good thing. The problem is you're shining the laser directly on the surface of the capsule, and it starts out solid density. And unless you have a super duper smooth beam, you tend to imprint the beam pattern on the capsule. I'm going to show you later on what can happen to imprinted perturbations. But with the hologram out here, yes, you've got uneven heating of the wall, but that doesn't matter. I'm on the capsule here looking outward. I see 2 pi steradians. I'll average over any short wavelength perturbations in the radiation. And I don't think I mentioned it, but in practice, you only really have to worry about the P2 and P4 Legendre component in terms of symmetry, because everything shorter wavelengths than that is smoothed out by the hologram. So we went for the hologram on the grounds that we didn't have to spend multiple years trying to figure out how to keep that imprint from the laser from killing you. But there's a lab at the University of Rochester that has a good laser, but less power than ours. And they are working on direct drive. And they have got some experiments on it, but they haven't had enough yet to get ignition that way. Once you got ignition, it would actually be great if you could do direct drive, because there's less prep in the target chamber. And you actually have to have your laser beams very well aligned with the hologram to get that P2 and P4 moment right. And so there will be issues there. And, they're talking about guns where they sort of spin the target to stabilize it as it goes in there. Nobody has demonstrated that one yet, to the best of my knowledge, but I think some of the startups are playing around with that. So they probably couldn't tell me, because until somebody else has done it and published, they want to keep a lid on that. So anyway, the capsule is suspended at the center of the hologram. The outer shell in most current experiments is made of high density carbon, which is sort of like diamond, but sort of many diamond grains instead of a uniform perfect crystal that you put on your finger. There's a layer of frozen DCT inside the outer shell. Central part of the target is filled with gaseous DT, and I suppose I might as well mention this at this point. How do I have gaseous and frozen DT in the same target? Why doesn't it all freeze out? Well, remember I said it's cryogenic. We actually get it at the triple point where the pressure, density, temperature allow you to have solid, liquid, and gaseous existing simultaneously. That is a constraint on the temperature you fire it at. And so if you've got a power plant, you're going to have to get that target from the target chamber wall to the center while still keeping it at cryogenic temperatures.
Why do you do that instead of just using all frozen or?
I'm going to come to the energetics in a minute, but the answer is we haven't got enough energy to heat enough fuel to the point where it ignites volumetrically. We can only get a small spark plug, we call it, in the center to ignite. And then the helium alphas deposit so much energy that it gets very hot and you get a traveling burn wave. And I don't know what you'd have to get yield, but it would be a huge capsule to try and just start spark plug. There are other schemes because this is so hard. One of them is not to have the gas in there and just let this frozen layer sort of converge, staying high density all the way. And then you zap it with a short pulse laser. Remember, this is 10 nanoseconds. That's long, right? And so you hit it with maybe 100 picosecond or something. And that creates a spark plug right there where that laser hits. But the intensity on that one is high enough that you got, relativistic electrons flying around, and electrons are pretty low mass and they're perfectly content to fly out into 4 pi steradians, but you want them to go straight forward to heat your hot spot. So nobody's doing that one yet. They're looking at it. But what we've got here was the safest way, in my opinion, to try and get ignition. I remain agnostic about what would be going on in a power plant, because it seems to me like there's quite a bit of work between where we are and a power plant. I would have said the whole thing was impossible based on the target fabrication, but then you go off and look at what the integrated circuit people have done. They're making enormous numbers of chips with 2 nanometer features, and they are actually getting pretty high yield. And this goes to show that if you had billions of dollars to throw at something, you can put a heck of a lot of engineering into it. Trying to do that in your lab, no way. But if you've got $1 billion and 200 engineers working on it, it's amazing things can happen. Typical laser pulse for the current targets is about 10 nanoseconds. 10 feet, which incidentally is less than the radius of the target chamber. So it finishes leaving the entrance portal before it actually hits the target. Fusion burn about 100 picoseconds. It turns out that NIF pulse shape control is an important part of producing ignition. I've said several times that I haven't got enough energy to do something, just haul off and whack it. I haven't got that much energy. We have to be clever. So the master oscillator generates separate low power pulses for each of the 48 quads and sends them to the amplifier chain. This is the chain is this thing I was talking about, where it's like 3 pass through the main laser glass. The ignition pulses start with a low intensity, then increase it to peak power. So that pulse shape drives 3 shocks through the target shell. That's both whatever plastic, carbon is left and the DT. It's 3 separate shocks there, but it's carefully timed. So this is one of the reasons I said we needed all those detectors. We couldn't time it without those detectors. So that the shocks coalesce just as they enter the DT gas. So the DT gas goes up to a very high temperature, but it's obviously no longer frozen by the time I've hit it with shocks. But the high density cooler DT is sufficiently cooler that you didn't put nearly as much energy per gram into that as you did in the spark plug in the center. So here's pictures of 3 different targets. In all of them, the capsule is suspended in the center. It's like you put a little very thin saran wrap or something on there, set the target on the top, put another one on the top, put the second half of the HORAM on it, and everything. If you're as good as our target fab people, stays where you put it. They obviously don't allow me to touch their equipment. So the thing to notice is that the one on the far left is using a CH ablator. That's what we started with on NIF. It has the advantage of somewhat higher hydrodynamic efficiency, which is a good thing, right? You're getting more work out of your available laser pulse. However, you need a longer pulse. And everything we've done so far with that, you get too much plasma filling of the whole round, and you start to get significant amounts of LPI, laser plasma interaction. And I'll come back to that later. So the two on the right are more like what we're using now. The one in the middle is probably pretty similar to the one where we got fusion ignition. If you look to the one on the far right, it's a bit bigger hole round and a considerably bigger capsule. So what you'd like to have a big capsule because then it has more surface area and can absorb more of those X-rays. But if you make it too big, it's out close to the hole round walls and the laser can't get up to the equator, or it does get up to the equator, but the blow off from the wall is so strong that it crushes the capsule and sends a pressure pulse in, and then things aren't round. So they think they can get away with making a target with that size capsule in the hole round. They're working their way upward. I don't think we've tried an ignition shot with that one yet. It'll be very interesting to see what kind of yield they can get. I haven't ever given you the pie diagram of the capsule, so arguably that should have been earlier, but here's where it's at. You can see the DT gas in the center, then the DT ice. There's this dope layer, and actually there was a little bit of pure high density carbon, then the dope layer, and then more high density carbon in our first ignition target. And the idea is that, I start a shock out here, it propagates inward, then I increase the power, that drives another shock with a higher pressure and therefore a higher velocity. So it's gaining on the first shock, and then finally I go up to the peak intensity, launch one more shock, and it's considerably faster, and I have compressed things enough that it doesn't have to go as far. And so they all come in and coalesce right here, just inside the DT gas. Now, the distinction between DT gas and DT ice is not preserved after these shocks go through. It's all DT plasma. But there is a reasonably abrupt transition from low density hot to high density cooler. And that's how we get the spark plug and propagating burn. All right, I mentioned possibility of a couple movies. So this one here is something that a couple of my buddies in the Visualization Center put together for me. So this shows the target chamber. You can see that there's potential of a lot of ports, but the only ones it's showing are the ones through which those 48 laser quads enter the target chamber. And now we're going to zoom a bunch, but let me point to the very center. You can see some, finger sticking down there. Well, the hole round is actually on the end of the finger. And so we're going to zoom far enough that you can see the hole round. And so there it is. Now, this isn't an accurate depiction of the target positioner, but nobody was paying my Viz buddies to do an accurate job of the target positioner. So you get the point, though, that you've got this capsule in here. There'll actually be a stalk that it's mounted on, so it's much more complicated. Okay, earlier I was talking about direct drive and the imprint of the laser on the capsule. Now, if I just run the laser light through the amplifier chain and I attempt to extract all the energy from the neodymium glass, I will wind up with hot spots within the beam. And the hot spots are big enough that they will mess up the implosion. So we don't do that. When I first came to Livermore, we were just commissioning the Nova laser, and there was one set of experiments where I said, here's what happened when we changed the laser spot size. It could be because that changes the average intensity. It could be because the beam quality improves as you defocus it. Or it could be that it's a two-dimensional effect. So the bigger the spot, the more 2D the target. I couldn't tell them apart. That beam was sufficiently crappy that there was nothing I could do about it. This one here is a different approach that was actually pioneered, I believe, at Rochester. You take a sheet of glass, we call it a phase plate, and think of it as laying out a bunch of pixels on it. It's actually, this big, so it's a very large pixel, but still many, many pixels. A random phase plate, you would go through rolling the dice. For each pixel, you either add half a wavelength of glass or you don't. And what you wind up with is actually an interference pattern between all those beams coming out of those little chunks of glass. And there are so many of them that it averages out and it's actually pretty smooth. You can see the speckles there. But if you're talking about the whole round wall or the outer surface of the capsule, they respond to things other than direct laser impingement on hydrodynamic timescales. And this thing has enough bandwidth in the laser that speckles flutter around over time. And so the whole round wall sees a very smooth beam. The target picks up very smooth radiation. Unfortunately, plasma doesn't know that it's supposed to average things. And it can respond faster than we can move the speckles around. So I have simulated many times the beams there, and that's the second talk that I'll be giving. And I actually have to account for the speckles when I do that. But if I were just doing a hydrodynamic simulation, I wouldn't, because it's operating on timescales where this is effectively smooth. So we're going to turn that off. You can see the capsule there in the center. And now, because they're biz guys, they're going to spin it around a little bit, enjoy themselves. But at this point, whoops, sorry. I'm going to stop it right there. I'm going to mention something. What I showed you on that earlier one was a single quad going through the entrance hole. There's actually 24 of them going through the entrance hole. This is going to be a movie, once again, showing a single quad. And what I'm trying to show you is that it's one of the what we call intercone beams that's supposed to wind up here on the all-around wall, close to the equator of the capsule. So that's the beam propagating in. This is not time zero. This is after I've reached peak intensity, because of course the plasma instabilities are stronger at higher intensity. I'm going to play this a little bit more. If you look closely in this region over here on the left of the beam, you'll see a little bit of flickering going on, not very much. So I'm just showing it again in case I talk so long that I forgot something. This was at a movie given at supercomputing. So I couldn't even rely on them knowing what a plasma was. Okay, so this is bursts of stimulated Raman scattering. So let's see if I can stop it there. So the laser intensity entering the hologram is smooth on these time scales. But the point where the gain rate is highest is back here by the wall, the high density, about quarter densities where Raman tends to occur. And so that starts out from a very small seed and then grows exponentially for a bit, but it's propagating back this way. And it turns out that you eventually go a bit off resonance. But in these experiments, the Raman light intensity had gotten so large that even though it was off resonance, it was still sucking energy out of the laser beam. And in point of fact, you could almost completely block the lasers. There was very little reaching the back. And so what you've got is a limit cycle powered by pump depletion. Now, this is back in the days when we had CH capsules, and I said that we had too much happening in the hologram, in the plasma. This is not what you would see if I simulated an ignition target. Only a small fraction of light, 5, possibly 10% is backscattered. It made life a whole lot easier. They'd still like to go back to the plastic targets, but they can't go there until I stop this. Now I'm going to go on and show the beryllium. It isn't particularly interesting here in the sense that it's not very strong. But there's a point I wanted to make, which let me get a little bit here. Okay, so this is a burst of beryllium. It's weak compared to the first one, the Raman. And basically, you've got competition between the Raman and the beryllium because the Raman is depleting the pump and the beryllium, scattering off of ion acoustic waves, is going to have to operate with the same pump. So it doesn't do much here.
Sorry, I don't know what this is. What is this radiation?
Okay, the blue stuff, if you start, okay, so here's something I probably shouldn't say, but I sat in on a plasma class when I was in grad school. I wasn't a plasma physicist at the time. And my somewhat facetious conclusion is that a plasma physicist is somebody with an instability for any occasion. So we've got filamentation instabilities that occur, both ponderomotively driven with light pressure and thermally driven. Thermally driven is more likely here. So that's one form of instability that I would simulate. You've got a 10 to the 15 watt per square centimeter laser, which is a coherent light source, which means it's all oscillating in phase. And so now you've got some electrons there, and you're shaking them up and down, up and down, up and down with a very serious electric field. And if you start shaking them at the electron plasma frequency, that's their natural restoration frequency, it stays in phase with the laser. It sucks out more and more and more energy, but it can't just suck out energy. It turns out it emits another photon back towards the laser, and you get a electron Langmuir wave going off to conserve momentum. And so that was the first one. Well, it turns out that the ions were upset that they didn't have an instability. Once again, I'm being facetious. And so there's a beryllium instability where you get an ion acoustic wave. This is, I mean, a sound wave, right? But you can get that be resonant with the beam too. And it doesn't go as fast. The one where I can't average stuff out from the speckles would be the Raman, because electrons just move faster than ions, and that's the end of it. But the beryllium is actually a problem, because when you bring it in and get the acoustic wave this way and the light that way, the acoustic wave is effectively quite massive. So it can absorb all of the momentum of the laser with hardly any energy absorbed. So the Raman photon is significantly longer wavelength. Instead of bluish, it's getting down towards greenish, I think. The beryllium one is damn near the same wavelength as the laser light. You can measure the shift, but unfortunately, if it propagates backward far enough through the laser chain, the optics, which expanded the beam on its way towards the target as it gained more energy, would start focusing it down. Fortunately, we've never blown up the laser glass, because we've always blown up the mirrors that direct the beams around in those 48 ports. However, it's considered bad form to destroy those mirrors, because then it can be like a week before you can replace them, and then you've lost those shots, and don't do that. So we actually have a review board that looks at all proposed NIF experiments. And if they're not sort of incremental modifications of an existing one, they try and figure out what's the likely level of plasma instability, particularly the stimulated beryllium, because the Raman just wastes energy effectively and mucks up your symmetry and reduces your energy. But the beryllium can actually damage the facility. And so I wound up simulating something which will probably show up in that next talk, where it would have been really nice if they called me in beforehand instead of just shooting it. Oh, that can't make any difference. They were repointing the beams within the hole round to try and control that P2 asymmetry that I mentioned. Unfortunately, in this particular hole round, when you repointed it from here to here, you actually got a period where it was skimming along the wall in a region where the laser was resonant with an acoustic wave. And so just that simple little repointing changed it from negligible backscatter to damaging. I think we took out 2 mirrors on that shot. And so when I went back and simulated it with the old pointing and the new pointing, the old pointing was sort of like this one. No big deal. The new pointing, whoops, don't do that. Sorry, we already did. And so you can do this with the simulation codes, check things like that out. And it's important, because we only get a few shots a day. And it's all kinds of people that want to do things, not just inertial confinement fusion. And so our management, really kind of scared about starting something new at full power. And so you usually have to ramp up. You might have been awarded 4 shots and you spend 2 of them ramping up. So it's like you only got 2 shots. And so if we could really guarantee that we could simulate the heck out of this and be exactly right, it would change the way we do things. Come on, there we go. So anyway, I'm going to let this go ahead and play on now. We're getting on there. So anyway, yeah.
It's a really main one, but then the reason why you don't have the diameter of the hole round equal to its height is one of the reasons is this. We can say that, right? All these instabilities of the beams contributing to it, so that we allow some space around there.
Yes, you have 4 cones, which, if you want to, you can say enter the target chamber at 4 different latitudes, and 4 more in the upper hemisphere. And they're at different angles. So the one that's at very nearly the angle of the hole round axis will wind up on the equator of the hole round. And the one that's furthest out will wind up much closer to the entrance hole. And so You spread those around, you aim them to try and get this uniform drive, but you also have to make sure that you don't get so much plasma piling up at the equator where the capsule blow off and the hole around wall blow off are very close together, that you can't actually get them where you're pointing them, that they stop in the plasma before the wall, and now you've changed your drive symmetry. And that is simply too much to control. You have to stamp that out instead of trying to predict that so precisely that you still wind up with a spherical implosion. It's not a promising idea. You better keep room for the laser to hit the hole on the wall.
And how about a rather oval one, like a curved one?
Yeah, so that one I mentioned where we damaged the laser glass was called a rugby hole round. There's nothing fundamentally wrong with it, simply that it's different and you can't actually trust, in terms of LPI, your earlier experience with the cylindrical hole round. We now got another one that sort of is one diameter on the outside and a different diameter in the middle, because it's, of course, just around the capsule we're most worried about. So if you pull the wall out a little bit there, but keep it in close somewhere else, you can potentially get a little bit more energy out of it. And we got a whole bunch of people running around trying to come up with ways to get more energy coupled to the target, given that at the moment we can't really increase the laser energy. So this is not an LPI simulation. This is using a radiation hydrodynamics code. And so you can see these little lines coming in through the entrance hole here at the end. So this is two quads here, and you can actually see them in the other hemisphere also. But this one, it was symmetric. So really, I'm only simulating half of the thing, which of course runs in half the time, which is why I was doing it. So as I mentioned earlier, a point on the capsule surface sees the whole wall. So you can see that the false color I'm using to indicate temperature on the inner wall varies. But because of that averaging, it's not nearly as bad on the capsule as it would be if you just looked at the wall itself. So Hydra is using ray trace to try and get the laser propagation through the plasma and deposition of energy at the hole wall. It cannot go after those speckles. I have run simulations, I think it was 3 laser quads, where I had 300 billion zones. And that would be trivial to the number of zones Hydra would need to deal with the speckles. And so I don't think Moore's law will hang around long enough that anybody will have a computer that can do that. So that's what we do for the laser. We have models for the emissivity from the hole around wall as a function of temperature and density and so on. We have radiation transport through that material to the capsule. If you want to know what the asymmetry on the capsule is, you propagate the X-rays in and just measure it. And so yes, it's pretty good, but it needs to be very good to get the kind of compression ratio I'm going to show you in a moment. And then obviously we got to have fusion reactions, right? I mean, how do you know you got fusion if you don't have fusion reactions? And so it's a very complicated code. I'm going to come back to it later. But this movie was based on Hydra. So I mentioned earlier, outer shell of, in this one, CH, we're currently using high density carbon. That's not shown in this movie. Well, actually, it's sort of shown indirectly in the movie. I'll come to that in a moment, but not in these frames. My DT gas is at the center, which is inside this, which is the DT shell. And so what I've got is radiation heating the capsule. It has to burn through the plastic or carbon before it gets to the DT shell. And it's set up so that the thickness of that shell is such that you would burn almost all the way through it at the point the laser pulse cuts off. So you're not ever actually deliberately burning off DT using the laser. So I've got, in the end, all of that carbon stuff is flowing outward at pretty high velocity. You've had a rocket exhaust effect on the remaining capsule, very high pressure. That's what's going on there. I'm going to flip back to the previous one, but look at the target there, the capsule. See, it's smaller, but the other thing, the walls were not white hot there, and they're now showing us white hot here. And so basically, this is not full power, but it's getting there. You can see that the wall, the whole room is more uniformly hot. It's all hotter. And I'll just briefly mention this. We have to keep this thing cryogenic, and so there's a membrane on the ends, some thin mylar or something. And then there is sometimes something lining the lip of the entrance hole. And so that stuff actually gets ablated by the edges of the laser beam. I don't have a perfectly sharp edge, so a little bit of it hits that. And so this bluish stuff here is started out here by the entrance hole and it's blown out. It's going to want to be blown out because I'm ablating wall and carbon, which is filling up the interior and is pushing out the helium that originally filled the hole up. So it's fairly complicated. Oops, come on. Sorry, it's jumping on me. So here I'm showing those were just frames. And so the Viz guys are playing around, but they come back to this bit where you show 24 quads going in, but that would be messy, so you only do 2, the simulation. Now I saw right there, they just peeled off the plastic, so you can follow the DT, which is the stuff that's all supposed to go inwards. And if that were to start increasing in radius, you would say, oops, and make the plastic shell thicker. Over here, you can see both the plastic and the DT. So a ways into the movie, you're going to see that plastic coming off to a much larger radius. That's why we worry about it going over there and hitting the wall. Right, at this point, it's still relatively low power. You can maybe, I don't know, see a little line here. You're not going to be able to do anything. I'll try and stop it once it gets above, far enough above that maybe you can see it. Right, you can sort of see a little step up there in intensity. I think this one is an early enough design that it had 4 pulses, and it's not what we used for ignition. You can also see it's getting hotter in here. And so you could keep an eye on that, but what's going to happen is all of a sudden it clearly gets very hot over here. But it's important to note that, as I said, the shocks move at different speeds. So the first pulse needs to be longer because that shock's going to be moving slower. The next one is going to move faster, and so you have to time them all. And in the end, you can see it's almost up to peak intensity there. It's not going to stay at peak intensity very long at all. Maybe a couple of nanoseconds. Okay, so now it's off, but notice the size of the capsule here. It's already imploded to a small fraction of its original radius. That surface is so small that it can't actually get any significant amount of energy through heating from the Horon wall. So when it gets that small, you turn off the laser, and you can see that the laser is dropping over here in the power versus time window. So it's all timed fairly precisely so that you burn through the shell and sort of turn off the laser simultaneously. We're zooming in on the capsule. This is going way too long. And so I'm going to let this mostly play through. Then this is the ignition. And so for a while, it was getting hotter, but the DT wasn't really moving outward. That was the dense, cooler stuff on the outside, the hot stuff that ignited in the middle. And then you dump so much heat in from those alpha particles that the pressure becomes truly enormous. It was pretty damn large when I fully compressed it, but now it's much larger, and whoosh, it all flies apart. But you've got the thing in the center up so hot that the fusion rate is very high, and it ignites the rest of it. So I may have to skip some of these or go into less detail, but
I wonder how many more slides do you have?
6 or 8, but I'm not going to worry about all of them.
Okay.
I'm just going to be asking you mostly to look at pictures.
Sounds good.
So this one here is, I mean, in some sense, punchline. We achieved ignition for the first time in 2022, and in 2025, we had an experiment that produced 8.6 megajoules of fusion energy from a 2.3 megajoule laser pulse. So if we ignore the inefficiency of pumping the laser, we've got gain. This one here, I commented several times about perturbations. So here we've done our best to get the perturbations down low, and yet you can see that this interface has become very distorted. And so it turned out that if you took this uniform dopant layer and had the dopant fraction ramp up, go flat, and ramp back down, you get much less growth of those perturbations. That's the one on the right. That was all based on simulations. We have nothing that can measure that in the imploded capsule. I mentioned Hydra earlier. It's a million line code. In other words, it's complicated. It has to be. These perturbations, yeah.
Are you doping it in like a symmetric way? Or
The doping should be spherically symmetric, but non-uniform in the radial direction. And we actually are doing a pretty good job of keeping it round. So we're not doing anything about trying to adjust for asymmetric drive by funny doping. There are stunts that you could pull, but NIF is flexible enough that you wouldn't have to. And so basically all of us figure this is complicated enough, and let's not grab any complexity we don't have to. So there's just one thing I'm mentioning here. If you look here on the left, 7.25, there's a perturbation that's pretty large inside, but the outer surface looks more like a golf ball, dimples. Go a little bit later, I'm starting to get spikes on the outer shell, and then this thing here has grown. Remember I said we've got this cryogenic target? Well, we had to fill it in place, and so we needed some way to get liquid DT into the center of the target, and so there's a fill tube. Well, that's the perturbation. Now, one other thing to notice in this particular simulation, that this thing is now somewhat taller than it is wide. It's prolate. Go a little bit later in time, the radius is smaller, but it's still prolate. And you can see that it's very non-symmetric here in the center, which is where the spark plug lies, the DT gas. And here at 8.3, which is only 120 picoseconds later, it's all of a sudden oblate instead of problate. And it's even more distorted. And what we would like to do is have it be essentially completely round at ignition. We didn't quite achieve that in this shot. But to some extent, if you balance out the prolate and oblate periods so that it comes in round, it's okay, but not precisely. So there's a gang running simulations and experiments seeing if instead of just averaging it out to be round, they can't keep it more nearly round all the way in. Yeah, so this is the last slide. We're currently working on ways to consistently achieve ignition. We're working on reducing asymmetries in the laser drive. That would keep it more nearly round all the way in. And the problem with it going up late is that you wind up with residual kinetic energy. It stops this way before it stops that way or something of that sort. So you'd like to fix that. Ongoing efforts trying to reduce the number and size of ball perturbations on the capsule. What they're doing now is really impressive, but if we get a batch of 50, there's maybe only 4 of them that you would use for ignition. You could do others for non-igniting shots, but for ignition, it really has to be good quality. We're looking to increase the laser energy. The more energetic the laser, the less you have to converge it. And so the reason those instabilities grow, they're hydrodynamic perturbations. Rayleigh-Taylor, probably the dominant one. You're decelerating that shell from 10 to the 7 centimeters to rest in maybe a couple hundred picoseconds. Well, try and guess what the deceleration is. It's a very large number, which means the growth rate is very high. But if you can keep it out further, it doesn't have to scream in as much to get to where you can ignite and burn. And so that's nice. There is room in the current laser building to put in a few more slabs of that neodymium glass. It would maybe be perhaps a 20% increase in energy, but we have learned that we can already damage the optics with the energy we have now. So we're going to have to be very careful if we get more energy that we don't start just blowing it up and we get 5 shots that are great and then the facility is down until we can get a few $1 million to replace laser glass or something. Nobody wants to go there. The other point is the startup companies are working on fusion power plant designs. There are several of them, and a number of my colleagues quit working for Livermore and went off to work for the fusion startups. So those guys, the venture capitalists, are throwing serious money into that. And I forget how many companies, there's maybe 4 of them, which is more money than venture capitalists have ever put into fusion before. So we think this is maybe on the verge of turning into something that has real world impacts, which is kind of cool after I've been there 40 years and having somebody notice what we're doing. All right. If there's any other questions, happy to take them, but we've run over by a fair bit.